So in lesson 3.7, we're going to go through more about lines. We've learned how to calculate slope. We've learned how to write equations of lines given that rate of change. And we're going to continue to kind of develop these ideas and work with them some more, and also get more comfortable with plotting them. So let's assume that we're in some student organization and we're planning a year-end pizza party to celebrate another year on campus. As chair of the planning committee, you've worked a deal with a local pizza place to provide large pizzas at $9 each. The budget will allow at most $175 to cover the food, and you want to figure out how many pizzas can you possibly get to stay under budget. So we're really going to go about this problem a bunch of different ways and kind of see advantages and disadvantages of both. The first thing we want to do is we want to figure out how many pizzas can we possibly get just using a numerical idea. So this is kind of our base point, and it's probably the one that's going to be the most natural that you want to do. But we're going to see how these other ideas all will revert back to the same concept. So you've got $175. Each pizza is $9. We might as well just see how many times 9 goes into the 175. So if we take the $175 and divide it by $9, this is around 19.4. So at most, we can get 9 pizzas. 19 pizzas. Okay. So we wanted to see how many times 9 went into the total amount. You can't buy a fraction of a pizza, so at most I can get 19. So now let's see if we can write an equation that represents the total cost of ordering C pizzas. And we want to see what does it tell us about how the cost varies when you change the number. So each pizza is $9, so we're letting C equal the cost. It's 9 times the amount of pizzas you order. So if you notice this format, we have our y is some constant times the other variable. So these quantities vary directly. So it has that special format. We order no pizzas, it's not going to cost us anything. So it's going to go through that origin. So now we're going to utilize this formula to estimate the number of, or we're going to utilize this formula to help us complete the table. And then in turn, we're going to see if we can estimate the number of pizzas we can buy. So we've got the formula that C is equal to 9p. So if we want the cost for 9 pizzas or 0 pizzas, we would take 9 and times it by 0. Cost you nothing for no pizzas. For 5 pizzas, it's $9 a pizza, so it's $45 for 5. For 10, $9 for each pizza, so it's $90. For 10 pizzas, the cost for 15 is 9 times 15, so it's $135. For 20 pizzas, you take 9 and times it by 20, so it costs you $180. And then for 25, you multiply it by 9, so it's $225 here. And then finally for 30 pizzas, you take 9 and times it by 30, so it's going to be 270 pizzas. So if we want to estimate from this, not knowing that we already know the amount, and we want to know we have a budget of 175, if we look right here, our budget is close to this amount. So that means I can get close to 20 pizzas. So you could probably think that, yeah, I can order we can order 19 still. So this is really, I know we already know exactly how many pizzas we've got, but it's kind of tying everything we've done in together. We've got this estimation, we've got this direct variation, and now I can get an approximation for how many pizzas we can possibly order. Okay. All right. So now let's use this information to draw a graph. We want to put the number of pizzas on the x-axis, and we want to put the cost on the y-axis. We want to pick an appropriate scale, and then we're going to use the graph to do the same to estimate how many pizzas we can possibly have. So we need to label everything. We went out to quite a few pizzas. I'm going to make it convenient. I'm going to make each one of these 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, and finally 20 pizzas at the end. And then we went up to a little bit more than 180 bucks. So I'm going to go up by $20 for the cost. So 20 bucks, 40, 60, 80, 100, 120, 140, 160, 180, and $200. So when we order no pizzas, it costs no money. 5 pizzas cost us $45. So that's going to be right around here. 10 pizzas cost us $90. So that's halfway in between the 80 and the 100. 15 pizzas is 135 bucks. So that's around right here. And then finally, 20 pizzas cost us $180, which is right here. So we can create our line by connecting all of these points. It's not perfect, but that's okay. So here's the line for pizzas. So the cost for number of pizzas. We want to spend $175. So that's close to the 180. If I draw a line over, that's going to be a little before 20 pizzas. So the same estimate we're going to get, we can say $175 is about 9 pizzas. So different way to get a similar estimate. So you can see it depends on the information you're given. If you're given the graph, you can use that to help you out. If you're given a table, you might be able to kind of reverse engineer things. But all of them do the same thing. You can find the same information a bunch of different ways. Okay. So now let's get back to kind of working with this more precisely. We want to spend at most $175. So that doesn't necessarily mean I want to get the most amount of pizzas possible. It just means I want at most this to be my budget. Maybe I really only need like 10 pizzas. Will that work? Am I going to spend more than this quantity? So because it has this word at most, it's a good place to use an inequality. So we're going to write one that can help us figure out how many pizzas we can buy. And we're going to solve that to then get our answer. So we want the cost to be at most $175. So the cost has to be less than or equal to 175. But the cost we know, it's 9 times the number of pizzas. So that's at most $175. So if you want to solve for the number of pizzas, you have to divide both sides by 9. And this gives us the number of pizzas is at most 19.4. So what this tells us is we can buy at most 19 pizzas. You can buy 8 and still be in budget. You could buy 12 and be in budget, but the most possible you can get is 19. But anything equal to this or less than 19, we are not going over our budget. Okay? So now let's go ahead and find the slope of the line that we drew previously. You can pick any points you want. Let's use when you sell no pizzas, it costs no dollars. When you buy 10 pizzas, it costs $90. So getting back to our slope, you look at the difference in y's. So we got 90 minus 0 divided by the difference in x's, so 10 minus 0. So this is 90 over 10, which is 9. So the slope is really just telling you that rate of change. It's $9 per pizza you get. Okay. And then in the case when we get our y-intercept, if we look back to the graph, we go right here through the origin. So the y-intercept, when x is 0, the y value is also 0. So this means when you buy 0 pizzas, it costs $0. Okay. And that's exactly this direct variation because none of the one thing means none of the other. Right. But now if we forgot about a delivery charge, then we've got to re-go through this. So now they're going to give us $9 per pizza still. And I'm going to have to pay $10 for them to bring all these pizza overs. So I still want to spend at most this $175, but now I got to figure out how many possible pizzas can I order. So if we want an equation now, my cost is still $9 times the number of pizzas, and then I have this flat fixed cost of $10. So I have to add 10 to it. Okay. So now when we go to actually figure out the cost per pizzas, we're going to do the same type of thing. I'm going to plug in these values of P into this equation. And then I'm going to use that to try to get an estimate before we figure out exactly how many we can buy. So when we plug in 0, we get 9 times 0 plus 10. So our total cost for 0 pizzas is now $10. So that means we've got that $10 fee regardless. When we buy 5 pizzas, we do 9 times 5 plus 10. So it now costs us $55, so 10 more than it previously did. For 10 pizzas, you take 9 times 10 and add 10. So it costs us $100 for 10 pizzas. For 15, you plug in P equals 15 and add 10, and it's going to cost you $145 for 15 pizzas. For 20 pizzas, it's going to be $190. For 25, it's going to be $235. And then for 30, it's going to be $280. Okay. So at most we can spend still $175. That's going to be somewhere between here. It's now not as close to 20. So it's probably somewhere halfway in between, maybe around 17 or 18 pizzas we can guess. Okay. So we're going to estimate we can get around 17 or 18 pizzas. Okay. So let's use this information and go ahead and draw it on a graph. And then we're going to again use that to see if we can see a better estimate. So I'm going to do the same thing as before. I'm going to make the number of pizzas go up by 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And then the cost, still going to go up by 20s. So 20, 40, 60, 80, 100, 120, 140, 160, 180, and 200. Okay. So now it's slightly different when we have no pizzas. Our cost is going to be $10. 5 pizzas is around 55, so it's around right here. 10 pizzas is $100. Wrong spot on that one. So 5 pizzas is around $55. 10 pizzas is $100. 15 pizzas is $145. So a little after 140. And then 20 pizzas is $190, which is right here. So we can connect our dots. And here is the cost for our pizzas. Again, I can still spend at most $175, so it's close to the 180 line. So here's the cost being $175. You hit the graph here, which seems like it's a little after 18. So we're going to assume that we can get about 18 pizzas. Okay. So we can buy around 18 pizzas. That's where we hit the graph at $175. Okay. So now let's actually go through and solve this. We'll write an inequality and then explain what that means after solving it. So the cost is still at most $175. But the cost is now 9 times the number of pizzas plus $10 for that delivery fee. So this is at most $175. So if we want to solve this, we've got to first isolate that variable by subtracting the p, but by subtracting the 10. So we get 9p is less than or equal to $165. So to find p, you now divide by 9, and this tells us that p is less than or equal to 18.3. So again, I can't buy 0.3 of a pizza, so we can buy at most 18 pizzas. Okay. So in this particular situation, does the cost of ordering pizza vary directly with the number of pizzas? And that's not going to happen here because I no longer go through that origin or 0, 0. Or another way I could see it is I don't have the cost is some constant times x. I have this additional $10 starting out fee. So no, it doesn't because of the delivery charge. Okay. So the graph doesn't go through 0, 0. And the equation isn't C is equal to some constant times the number of pizzas. So we have that extra fixed fee. Right. Well, let's go ahead and try to calculate the slope again. Now we have the point when we sell or when we buy no pizzas. It costs $10. And if you pick another point, say 10 pizzas, the cost is $100. The slope is the difference in y values, so 100 minus 10, divided by the difference in x values. So remember, you have to stay consistent with the order. The 110 go together, and then the 0 and 10 go together. So you have to keep the same order. So this is equal to 90 over 10, which is still $9. So the slope still tells us the same information. It's that rate, it's $9 per pizza. But our y-intercept is no longer 0, 0. The y-intercept is 0, 10. So this tells us there's the $10 charge before adding on any pizzas. Okay. So that y-intercept is still my cost when I have no pizzas. Okay. So this is kind of a really key concept. The slope was always $9 regardless of what it was. And then in the last one, the y-intercept was 0, 10. The equation for our cost was 9 times the number of pizzas plus 10. So this form is a very particular form. The slope is what goes attached to the variable. And this value at the y-intercept is that fixed initial starting value. So what we've had before is our output is the starting quantity plus this constant rate of change times the input variable. This is also called the slope-intercept form. So it's y equals mx plus b. M is going to be the slope and b is the value of the y-intercept. So another way you can write an equation of the line is if you know the slope and the y-intercept, it's just y equals mx plus b. Okay. So now let's utilize that we know that to make things a little bit simpler instead of trying to calculate and rewrite everything. A small business had just 12 employees when they opened their doors, but have been adding employees at a rate of 4 per month since then. We want to write an equation that describes the number of employees in terms of the number of months after the company was founded. So we've got a few unknowns. We have the number of employees, so let's call that E. And then the rate deals with months, so let's let M equal the number of months since the opening. Then the number of employees in the company is that initial 12, and your rate is 4 times the number of months. So this is that slope-intercept form. The slope is 4, and the y-intercept is 12. So the slope is equal to 4, it's our rate, and the y-intercept is equal to 0, 12. So it is a point. Okay? So the slope is telling you that the number of employees increases by 4 per month. And the y-intercept tells us at 0 months, there are 12 employees. So now, instead of having to go through finding a bunch of different points to be able to graph this, we can utilize these two pieces to our advantage. We know the slope, we know the y-intercept. The slope is telling us how much I'm increasing for every single month. So we're going to go ahead and graph this equation. On the x-axis, we're going to put the number of months that the company is open. And on the y-axis, we're going to put the number of employees. And so I'm going to start with 0 months, and I'll just go up by 1 to make it easy to graph. And then because the employees really just go up by 4 every month, I'm going to make these all go up by 4. So 4, 8, 12, 16, 20, 24, 28, 32, 36, and 40. You could pick a different scale, but since each one of these months I'm going to go up by 4 more, I might as well just use multiples of 4. Okay. So now we're starting out at 12 employees. So at 0 months, we have 12 employees. After 1 month, I've gained 4 more. So now I have 16. After 2 months, 4 more. Got 20, 24, 28. I'm going to go up each and every time by 4. So this is what our graph of our line looks like. Okay. So it makes it much quicker. I don't need to go through the process of making a table first. So this kind of gives you an overview. As soon as you know a line, there's a much more convenient way to graph it. You're going to plot the y-intercept. So your first coordinate's always 0, and then the y value is your initial starting. You want to find one other point on the graph, so either by plugging it into the equation or using that slope. So like in the last example, our slope was 4, which is 4 over 1. You're going to increase the y value by 4 for every x value that increases by 1. And then you just draw a line of those points you plot. Okay? So let's get some practice working with some other types of lines. We're going to work with blood alcohol concentration. So the legal limit when you're operating any type of car or motor vehicle is 0.08. So pretty much that means you're going to have alcohol that's going to get into your bloodstream the more you drink. So the 0.08 legal limit means 0.08% of the person's blood is going to be alcohol. So based on the percentage of alcohol in your blood, you're going to have different effects for drinking. So if you have more than 0.5% of your blood being alcohol, you're going to die from it. If you have close to that, so 0.4%, you could have coma, you could have death. 0.3%, a whole bunch of other things, tremors, memory loss, lots of stuff going on. So after that legal limit, it starts to get troublesome. So we're going to work with some particular people. And see if we can answer some questions about what's going on. So after being arrested for driving under the influence, a well-known starlet was found to have 3.5 times the legal limit of alcohol in her blood. And we want to figure out what is her blood alcohol concentration. So that legal limit is 0.08%. So this is our legal limit. She had 3.5 times that amount. So we're going to take this and multiply it by 3.5. So that's going to be 0.28%. So what this means is 0.28% of her blood is straight alcohol. So at that time, she had 0.28%. She falls in between this 20 to 30 range. So some symptoms she was experiencing was trouble walking, double vision, nausea, and vomiting. So this was everything going on when this lovely little starlet was pulled over. So she had trouble walking, some double vision going on, so seeing a couple of the officers simultaneously. She was nauseous, and she was probably throwing up. Okay. So not a very pretty sight at all. Okay. Now a different person, which we're going to call John Q. Bonehead, decided it would be a good idea to drive when he shouldn't have. But he did get pulled over before anything happened. So when he does get pulled over, it's found out that he has a blood alcohol concentration of 0.16 at 2 o'clock in the morning. So if you think of any other type of drug, it usually leaves your body at kind of an exponential rate. But alcohol actually leaves your bloodstream at a constant rate. So if you monitor it, every single hour, it's going to go down by that same amount. So for this particular guy, at 0 hours, his blood alcohol concentration was 0.16. After 1 hour, then it was at 0.145. 2 hours, it kept going down. 3 hours, 4 hours. So we have a bunch of different points for what's going on. So we want to see what is the slope of the line describing John's blood alcohol concentration, and what does it tell us? So you can pick any points you want. Let's pick it to be easy. Let's do after 0 hours, his BAC is 0.16. And after 1 hour, his BAC is 0.0145. So we have to stay consistent. If we put the 0.145 first in the top for our Y values, you've got to put that first for the X values. So these two belong together. Then we would group these two as well. So they would go here. So we put the Y value up top, which is 0.16, and then 0 in the bottom. So if you take 0.145 and subtract 0.16, you're going to get negative 0.015 over 1. So this is negative 0.015. So it's negative because it's decreasing. So this is telling us that John's blood alcohol concentration decreases by 0.015% per hour. Okay. Now our y-intercept for this graph after 0 hours is 0.16. So this just tells us that John's blood alcohol concentration started at 0.16%, right? And then it's decreasing by this constant amount each time. So if we want the equation, our slope, m, is the negative 0.015, and the value of b is that y-intercept. It's starting out at 0.16, okay? So this tells us the value y, which is his blood alcohol concentration, is the slope, negative 0.015, times the time after 2 a.m., plus that y-intercept, which is 0.16. So when using an equation to model a situation, it's important to recall what specific information provides. So we want to restate the answer to question 6 in the form of a statement. So if X represents the number of hours after 2 a.m., kind of color code this. This first piece is X is the number of hours after 2 a.m. Then Y, which equals negative 0.015x plus 0.16, represents his blood alcohol concentration after X hours. Let's do that in green. So this equation represents John's BAC after X hours. Okay. So this next question we're going to get to ignore because we're not really doing anything with graphing calculators, so don't worry about it. Okay. Let's move on to the next one. So now we've got this equation. I'll rewrite it up top. Y is equal to negative 0.015x plus 0.16. And X is the number of hours after 2 a.m. So we want to see what is his concentration of alcohol in his blood at 3:30 in the morning. So we need to figure out our value of X. 0 corresponds to 2 a.m. because that's when he got pulled over. So 3:30 is an hour and a half later. So 3:30 a.m. is 1.5 hours after 2 a.m. Right. So we want to plug in X is 1.5. So that's negative 0.015 times 1.5 plus 0.16. So at 3:30 in the morning, his blood alcohol concentration has decreased a little to 0.1375%. Right? So if we want to see how long would it take for him to drop below the legal limit, we basically want to see when is his blood alcohol concentration less than this. So we want to set up an inequality. We want his blood alcohol concentration to be less than the legal limit. And this would tell us how long he would have to wait to drive. So his blood alcohol concentration is negative 0.015x plus 0.16. This needs to be less than 0.08. So if we want to solve for this, you want to get the X and the variable on its own. So let's subtract the 0.16 from both sides. And that gives us negative 0.015x is less than negative 0.08. Okay. And then you want to divide by the constant out front to get X on its own. But you have to remember when you divide an inequality by a negative number, the sign has to flip. So now it becomes X is greater, and if you divide these two, it's going to be around 5.33. So what that tells us is he needs to wait 5.33 hours before his BAC is under 0.08%. So he has to wait that long until he's under the legal limit. Okay. All right, so now we need to figure out what information we'd actually need to draw this line. We do have it all. So you can do two things to graph it. You either need 2 points to be able to connect the dots, or you need the slope and the y-intercept. Or a point, really. Okay? If you have either of these two pieces of information, you're going to be able to graph the line. So let's give it a try. We've got the hours after 2 a.m. and his blood alcohol. So remember, our y is equal to negative 0.015x plus 0.16. So I'm going to go by 2 hours for each of these. Let's do 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. And then for his BAC, I'm going to go up by 0.02. So 0.02, 04, 06, 08, 0.10, 0.12, 14, 16, 18. So we know after 0 hours, his blood alcohol concentration starts at 16. Then we know the slope is negative 0.15. So after 1 hour, or after 2 hours, he would be at around 0.13. Okay. And once we have 2 points, we can connect our line, and here would be the line that talks about his blood alcohol concentration. Okay. And you could pick other points from the chart that we had. So you could pick other points from the chart we had, but after 2 hours, his BAC was at 0.13. Okay. So now we want to figure out what is the x-intercept. So we want to figure out, when do I intercept the x-axis, and what does that actually mean? Our y-intercept causes x to be 0. So we have our equation y equals negative 0.015x plus 0.16. If you want to intercept the x-axis, the y is going to equal 0. And you want to solve for the value of x that makes this equation true. So we need to go ahead and subtract the 0.16 from both sides. And so we get negative 0.16 is negative 0.015 times x. And then finally, to get x on its own, you divide by that negative 0.15. Okay. So this gives us that x is around 10.67. So the x-intercept is 10.67, 0. So if y is 0, that's telling you your blood alcohol concentration. So this means it will take 10.67 hours for his BAC to reach 0. So that's how long it will take for all of the alcohol to leave his system. So we have this connection between the value of the slope and the direction of the line. So when the slope of the line is positive, then the y values are increasing as the x is increasing. When the slope's negative, it's doing the opposite. So you see it's kind of going downwards. So if we look at a couple different examples, let's try to draw an example of a line with a positive slope. a line with a negative slope, and then finally a line with no slope. So here's x values, y values, x values, y values. Okay. So a positive slope means the y values are getting bigger and bigger and bigger as x gets bigger and bigger. A negative slope would mean those y values are decreasing. And then something with slope 0 would never change. So the y value just stays constant.